there is a feeling that settles over you when you begin to realize that the place you occupy might be unusual. Not in a dramatic way, not in a way that announces itself with fanfare or urgency, but in a quiet, persistent way that changes everything you thought you understood about where you are and what you are seeing. It is the feeling of standing in a room you have been in many times before and noticing, slowly, almost reluctantly, that the walls are not quite parallel, that the floor slopes gently in a direction you had not perceived until this moment, that the light coming through the window is refracted in a way that makes everything appear slightly different from how it would appear if you were standing somewhere else, in some other room, under some other sky. And once you notice this, once you become aware of it, you cannot stop seeing it. Every measurement you take, every observation you make, every calculation you perform carries with it the subtle signature of your particular vantage point, your specific location in a vast and complex space that extends far beyond what you can directly perceive. We live in a place. This seems obvious, almost trivial, the kind of statement that does not need to be said because everyone already knows it. But it is worth saying aloud, worth letting the words settle in your mind and rest there for a moment. We live in a place, and that place is not random. It is not arbitrary. It has properties, characteristics, a structure, and a history that make it what it is. It has a density, a distribution of matter, a gravitational landscape shaped by billions of years of cosmic evolution. It's part of a larger pattern, a cosmic web of galaxies and voids and filaments that stretches across billions of light years in every direction. A pattern so vast that we can only see a tiny portion of it, a small patch of the whole, but a patch that contains within it clues about the larger structure, hints about the nature of the cosmos beyond our horizon. And the place we occupy, the region of space that contains our galaxy and thousands of neighboring galaxies, the volume of the universe that we can study in detail because it is close enough that light from it has had time to reach us. This place appears to be different from the average. It appears to be less dense, emptier, more sparse than the typical region of the universe. It appears to be what astronomers call a void, or more precisely, an underdense region, a place where matter is spread out more thinly than it is elsewhere, where galaxies are fewer and farther between, where the gravitational pull of matter is weaker, where the expansion of space proceeds more quickly because there is less mass to slow it down. And if this is true, if we really do live inside such a region, inside what some researchers have called the KBC void, named after the initials of the astronomers who first proposed it, then everything we see, everything we measure, everything we infer about the universe is filtered through that context. The light reaching us from distant galaxies has traveled through this underdense region, and its journey has been affected by the lower density, by the faster expansion, by the weaker gravitational fields it encountered along the way. The structures we see forming around us, the galaxies and clusters and superclusters, are shaped by the particular environment they grew up in, an environment that is quieter, more sparse, less dynamically active than the environment in denser regions where galaxies interact more frequently and where the pace of evolution is faster. And this means that when we try to understand the universe as a whole, when we try to build models that describe how it began and how it evolved and what it will become, we are doing so from a perspective that might not be representative. We are observers inside a deviation, inside an anomaly, trying to infer the properties of the whole from measurements taken in a place that is, in some subtle but important way, atypical. And this realization does not overturn everything we know. It does not mean our models are fundamentally broken, or that our understanding is completely wrong. But it does mean that we need to be careful, that we need to account for our location, that we need to consider how our measurements might be biased by the fact that we are not observing from an average place, from a typical point in the cosmic web, but from somewhere unusual, somewhere that distorts our view in ways that are only now beginning to become clear. This idea, this notion that our cosmic address matters, that where we are affects what we see, opens up a landscape of questions, a terrain of subtle mismatches, and quiet puzzles that extend far beyond the simple fact of living in an underdense region. It touches on everything. It touches on how we measure distances, how we calculate the ages of galaxies, how we interpret the redshift of light, how we understand the formation of structure, how we model the expansion of the universe. It touches on the very foundations of cosmology, on the assumptions we make when we try to translate our local observations into global truths about the nature of the cosmos. Let us begin with something that feels solid and reliable, something that seems like it should be the same everywhere, independent of where you are or what you are looking at. The speed of light. Light travels at a constant speed, roughly 300,000 kilometers per second, and this speed is the same everywhere in the universe, as far as we can tell. It does not change depending on where you are, or how fast you are moving, or what direction you are traveling in. This constancy is one of the foundations of modern physics, one of the pillars on which our understanding of space and time is built. It is woven into the structure of Einstein's theory of relativity, into the way we define distances and measure time, into the very fabric of the cosmos. And because light travels at a finite speed, not instantaneously, but at a rate that can be measured and predicted, when we look out into the universe, when we point our telescopes at distant galaxies and capture their light, we are not seeing those galaxies as they are in this moment, in the present, but as they were in the past, when the light we are now detecting first left them and began its long journey through space. The light from a nearby star left that star years ago. The light from a galaxy, across the room of the cosmos, so to speak, left that galaxy millions of years ago. The light from the most distant galaxies we can see, galaxies at the very edge of our observable universe, left those galaxies more than 13 billion years ago, when the universe itself was still young, still in the early stages of its evolution. We are seeing the universe not as it is, but as it was, scattered across time, a mosaic of different moments all arriving at once, here, now, in the quiet darkness of the night sky above us. And this gives astronomy a unique character, a quality that sets it apart from almost every other science. We are not studying the present, we are studying the past, reaching back through time with our instruments, with our telescopes and our detectors and our careful measurements, trying to understand what happened long ago, far away, in places we can never visit, in moments we can never experience directly. But here's the thing, the complication that makes everything more interesting and more difficult at the same time. As light travels through space, Space itself is changing. The universe is not static. It is not frozen in place like a photograph. It is expanding, and it has been expanding since the very beginning, since the moment we call the Big Bang, when the universe emerged from a state of extreme density and temperature and began its long journey of cooling and spreading and evolving into the structured, star-filled cosmos we see today. Galaxies are moving away from each other, not because they are traveling through space like ships sailing across an ocean, but because space itself is stretching, expanding, carrying them along like corks, floating on the surface of a river that is growing wider and wider as it flows. And as space expands, the light traveling through it is stretched as well. The wavelengths of the light increase, shifting toward the red end of the spectrum, toward longer wavelengths, lower frequencies, lower energies. This phenomenon is called redshift, and it is one of the most important tools we have for measuring distances in the universe and for understanding its history. By measuring how much a galaxy's light has been redshifted, by comparing the wavelengths we observe to the wavelengths the light had when it was emitted, we can determine how much the universe has expanded during the time the light has been traveling. And from that, we can calculate how far away the galaxy is and how long ago the light left it. But the expansion is not perfectly uniform. It's not the same everywhere. It varies from place to place, depending on the density of matter, the strength of gravity, the presence of dark matter and dark energy, the local environment, the history of that particular region. In regions where matter is more densely packed, where galaxies and clusters are abundant, where the gravitational pull of mass is strong, the expansion is slower. Gravity resists the expansion, pulling things together, trying to create structures, trying to form galaxies and clusters and filaments. In regions where matter is sparse, where there are fewer galaxies, where the density is lower, where the gravitational influence is weaker, the expansion is faster. Space stretches more freely, unimpeded by the gravitational drag of matter, expanding at a rate that is higher than the average rate of expansion across the universe as a whole. And if we live in such a region, if we live in a place where the density is lower than average, where the gravitational pull is weaker, where the expansion is faster, then the expansion rate we measure locally in our immediate cosmic neighborhood might not be the same as the expansion rate averaged over the entire universe. Our local measurements might be biased, skewed by the particular properties of our location, and this could introduce systematic errors into our calculations, into our models, into our understanding of the cosmos. And this is not just a theoretical possibility, not just an abstract concern that exists only in the realm of mathematical models and computer simulations. This is something that might actually be happening, something that might actually be affecting our observations in measurable ways. When astronomers measure the expansion rate of the universe using nearby galaxies, using supernovae and other distance indicators, objects that we can observe in detail because they are relatively close to us, they get one number, one value for the expansion rate, a number that is usually expressed in units of kilometers per second per megaparsec. But when they measure the expansion rate using the cosmic microwave background, the faint glow of radiation that fills the entire universe, left over from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space for the first time, they get a different number, a different value. one that is significantly lower than the value obtained from nearby galaxies. This discrepancy, this tension between two different measurements of the same fundamental quantity, has been one of the most puzzling and persistent problems in cosmology for years now. It is called the Hubble tension, named after Edwin Hubble, the astronomer who first discovered that the universe is expanding, and it has resisted all attempts to explain it away as a simple measurement error or a statistical fluke. Both methods have been checked and rechecked, refined and improved, scrutinized by countless researchers, and the discrepancy remains. The numbers do not match. The expansion rate measured locally is higher than the expansion rate inferred from the early universe, and no one is quite sure why. And one possible explanation, one hypothesis that has been gaining attention and credibility in recent years, is that we live in an underdense region, and that the local expansion rate we measure is slightly faster than the average expansion rate of the universe as a whole. The underdensity creates a kind of bubble, a region where space expands more quickly because there is less mass to slow it down. And this affects our measurements, creating a mismatch between what we see locally and what we infer from the distant universe, from the cosmic microwave background, from the large-scale structure, from the patterns and signals that come to us from regions far beyond our immediate neighborhood. This is a subtle effect, a gentle deviation, not a catastrophic error or a fundamental breakdown of our understanding, but it ripples outward, touching everything we observe, influencing every calculation we make, distorting every inference we draw about the nature of the cosmos. Because if the expansion rate is different here, if our local measurements are biased by our location, then the distances we calculate are slightly off. And if the distances are slightly off, then the ages we assign to distant galaxies are slightly off. And if the ages are slightly off, then the masses and the luminosities and the formation times and the evolutionary histories we reconstruct are all slightly distorted, filtered through the lens of our unusual location, shaped by the particular properties of the region we happen to inhabit. And there are hints scattered through the data like breadcrumbs on a forest path that something like this might be happening, that our observations are indeed being affected by our location in ways that are only now beginning to become clear. When astronomers look at the most distant galaxies, the ones whose light has been traveling for billions of years, crossing vast stretches of the expanding universe to reach us, they sometimes see galaxies that appear too mature, too massive, too well organized for their age. According to our models, according to the simulations we run and the theories we have developed, these galaxies should still be in the process of forming, still chaotic and irregular, still accumulating mass, still in the early stages of their evolution. But they look like galaxies that have already gone through billions of years of development. Galaxies that have settled into stable structures, with rotating disks and spiral arms and central bulges, with populations of old stars and well-established patterns of star formation. How is this possible? How can a galaxy appear older than the time that has passed since the universe began? How can it look so mature, so evolved, so organized, when the clock of cosmic time says it should still be young and unformed? One possibility, the one that most researchers initially consider, is that our models are incomplete, that galaxies can form more quickly than we thought, that there are processes we have not accounted for that allow structure to emerge faster, that allow stars to form more efficiently, that allow galaxies to assemble and organize themselves on shorter timescales than our simulations predict. But another possibility, one that becomes more intriguing the more you think about it, is that we are misinterpreting what we see, that the light from these galaxies has been affected by its journey through space in ways that we have not fully accounted for, that the expansion, the redshift, the gravitational influences along the way have all conspired to make these galaxies appear different from how they actually are. And if we live in an underdense region, if the light from these galaxies has traveled through a region where the expansion is faster, where the density is lower, where the gravitational landscape is different, then the redshift might be slightly different from what we expect, and this would change how we calculate distances and ages and masses. It would introduce a systematic error, a quiet bias, a subtle distortion that makes distant galaxies appear older and more massive and more evolved than they really are. And this is just one example, one piece of a larger pattern, one thread in a tapestry of mismatches and inconsistencies and quiet puzzles that are scattered throughout our observations of the universe. There are other anomalies, other subtle discrepancies, other ways in which what we see does not quite match what we expect. There are galaxies whose velocities do not quite fit the patterns predicted by our models of how matter is distributed and how gravity shapes the flow of galaxies through space. There are clusters of galaxies that seem to be moving in unexpected directions, flowing toward regions we cannot directly see, pulled by gravitational influences that are not accounted for in our maps of the cosmic web. There are patterns in the distribution of galaxies, alignments and correlations that extend across enormous distances, far larger than we would expect if galaxies were simply responding to their local environment, to the gravitational pull of nearby structures. There are hints of large-scale flows, coherent motions of vast numbers of galaxies, all moving in the same direction, as if they are being pulled by something massive and distant, something beyond the edge of what we can observe, something that lies outside our cosmic horizon. And all of these mismatches, all of these quiet puzzles, all of these subtle inconsistencies might be connected. They might all be symptoms of the same underlying reality. The fact that we are observing the universe from an unusual place, a place where the density is lower, where the expansion is faster, where the gravitational landscape is different. And this changes how we interpret everything. It changes how light travels, how it is redshifted, how it is bent by gravity, how it carries information about the objects that emitted it. It changes how structures form, how galaxies evolve, how the cosmic web assembles itself over billions of years. It changes the very framework within which we understand the cosmos. Think about gravitational lensing, one of the most powerful tools we have for studying the universe, for mapping the distribution of matter, for detecting the presence of dark matter, the invisible substance that makes up most of the mass of the universe, but does not emit light. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity. The idea that massive objects bend space and time around them, and that this bending affects the path that light takes as it travels through the universe. When light from a distant galaxy passes near a massive cluster of galaxies, the gravity of the cluster bends the light, distorting the image of the background galaxy, creating multiple images, or arcs or rings, patterns that we can observe and measure and use to infer the distribution of mass in the cluster. By studying these distortions, by comparing the observed patterns to what our models predict, we can map the distribution of mass in the cluster, including the dark matter, the invisible component that does not emit light, but whose presence is revealed by its gravitational influence. We can test our understanding of gravity, of dark matter, of the structure of the universe. We can weigh clusters, measure their masses, study how they have grown and evolved over time. But gravitational lensing depends on the density of matter along the path the light travels. If the light passes through a region where matter is densely packed, where there are many galaxies and clusters, where the gravitational fields are strong, the bending is pronounced, the distortions are large, the effects are easy to see and measure. If the light passes through a region where matter is sparse, where there are fewer galaxies, where the density is lower, where the gravitational fields are weaker, the bending is subtle, the distortions are small, the effects are harder to detect. And if we live in an underdense region, if much of the light reaching us has traveled through a region where the density is lower than average, then the gravitational lensing we observe might be weaker than we expect. The distortions might be subtly different. The patterns might not quite match the models. And this would introduce another layer of complexity, another source of mismatch between theory and observation, another way in which our unusual location affects what we see and how we interpret it. And there is something almost poetic about this, something deeply humbling and thought-provoking. We are trying to understand the universe, to map its structure, to trace its history, to predict its future. And we are doing this from a single location, a single vantage point, embedded in a cosmos so vast that our entire observable universe, everything we can see with our most powerful telescopes, is just a tiny patch, a small region within a larger whole that extends far beyond what we can ever hope to observe directly. And that patch, that region we can see, might not be representative. It might be skewed, biased, shaped by the particular properties of our location, by the fact that we happen to live in a place that is, in some way, unusual. And this means that our measurements, as precise as they are, as carefully as they have been made, are not measurements of the universe as a whole, not measurements of some objective, universal truth, but measurements of the universe as it appears from here, from this particular place, filtered through the lens of our specific location in space and time. They are local measurements, and we are trying to use them to infer global properties, to understand the whole from a part, to extrapolate from the particular to the universal. And this is a delicate task, a task that requires care and caution, and a willingness to consider how our perspective might be shaping what we see. Imagine for a moment, if you can, that you could move, that you could travel to a different part of the universe, to a region where the density is higher, where galaxies are packed more closely together, where clusters and superclusters are abundant, where the expansion is slower because the gravitational pull of matter is stronger. What would the universe look like from there? Would the night sky appear the same? Would the cosmic microwave background have the same temperature, the same pattern of fluctuations? Would the distribution of galaxies appear the same? Would the expansion rate you measure be the same? Would the redshifts you observe match the redshifts you observe from here? Probably not. Almost certainly not. The universe would look different because the local conditions would be different. The light reaching you would have traveled through different regions, been influenced by different gravitational fields, been stretched by different expansion rates. Your measurements would be different. Your calculations would yield different results. Your models would be shaped by different data. Your understanding of the cosmos would be influenced, perhaps even determined, by the properties of that new location, by where you are and what that place is like. And this raises a question that is both scientific and philosophical, a question that sits at the boundary between empirical observation and conceptual reflection. When we talk about the universe, what do we mean? Do we mean the universe as it actually is, in some objective sense, independent of any observer, independent of any particular perspective? Or do we mean the universe as it appears to us from our particular location, with all the biases and distortions and filters that come from observing from an unusual place? The answer, perhaps, is that there is no single universe in the abstract sense, no view from nowhere, no perspective that is not a perspective. There is only the universe as observed, the universe as measured, the universe as interpreted through the lens of a specific location, a specific set of conditions, a specific point in space and time. And different perspectives, different locations, will yield different pictures, each one valid in its own context, each one true in its own way, but none of them capturing the whole truth, none of them giving us a complete, unbiased, universal view of the cosmos. And this is not a failure. This is not a limitation that we need to overcome, or a problem that we need to solve. This is simply the nature of observation, the nature of being embedded in the thing you are trying to understand, the nature of trying to comprehend a whole when you can only ever see a part. We cannot step outside the universe and look at it from the outside, from some privileged vantage point that is not itself part of the cosmos. We can only observe it from within, from our particular place, and try to account for how that place shapes what we see. Try to correct for the biases. Try to infer the properties of the larger whole from the limited, local measurements we can make. And the more carefully we account for our location, the more accurately we can model how our observations are affected by where we are. The closer we come to understanding the universe, not just as it appears from here, but as it actually is in some deeper, more objective sense. But accounting for location is not simple. It is not straightforward. It requires detailed models of how matter is distributed, how light travels through varying densities, how the expansion changes from place to place, how gravitational fields affect the paths of photons, how redshifts are influenced by local conditions. It requires understanding not just the average properties of the universe, the mean density, the typical expansion rate, the general patterns of structure, but also the deviations, the fluctuations, the local variations that make each region unique, each place different, each observer's view distinct. And this is a vast, complex task, one that we are still in the early stages of understanding, one that will require years of careful work, detailed simulations, precise observations, patient analysis. But it is also a task that is deeply rewarding, intellectually satisfying, full of surprises and discoveries and moments of insight that deepen our understanding and expand our sense of what the universe is and how it works. And there are layers upon layers to consider, complexities within complexities, subtleties that reveal themselves only when you look closely, when you think carefully, when you refuse to accept simple answers and demand to know more. The universe is not just expanding, it is also evolving. Galaxies are forming, merging, changing over time. Stars are being born in clouds of gas and dust, living out their lives, dying in explosions that seed the cosmos with heavier elements. Black holes are growing, consuming matter, releasing energy, shaping the environments around them. Dark matter is clumping together, forming halos that pull ordinary matter along with them, creating the gravitational scaffolding on which galaxies form. And all of these processes are happening at different rates in different places, depending on the local density, the local environment, the history of that particular region. In a dense region where galaxies are packed closely together, where clusters and superclusters are abundant, interactions are common. Galaxies collide and merge, triggering bursts of star formation, disrupting their structures, creating new configurations. Gas is heated and compressed, falling into galaxies, fueling star formation, and feeding black holes. The environment is dynamic, active, constantly changing, full of energy and motion. In a sparse region, where galaxies are more isolated, where the density is lower, where interactions are rare, the evolution is different. Galaxies evolve more quietly, more slowly, shaped more by their internal processes than by external influences. Star formation proceeds at a steady pace, without the dramatic bursts triggered by collisions. Black holes grow more gradually, fed by a trickle of gas rather than a flood. The environment is calmer, more stable, more predictable, less subject to the chaotic disruptions that characterize denser regions. And if we live in a sparse region, if we inhabit an underdense bubble in the cosmic web, then the galaxies we see around us, the structures we study in detail, the objects we observe with our telescopes, might not be representative of galaxies elsewhere, might not be typical of the universe as a whole. They might be different in subtle ways, shaped by the quiet environment they have grown up in, evolving according to rules that apply in sparse regions, but not in dense ones. And when we try to build models of how galaxies form and evolve, models based on studying the galaxies we can see in detail, the galaxies in our local neighborhood, those models might not apply as well to galaxies in denser regions, where the conditions are different, where the processes are different, where the outcomes are different. And this is another layer of complexity, another source of mismatch, another way in which our location affects our understanding. When we look at distant galaxies, at galaxies in the early universe, we are often looking at galaxies in denser regions, regions where structure was just beginning to form, where matter was still clumping together, where the environment was more chaotic, more dynamic, more active, and those galaxies might behave differently from the galaxies we see nearby. Not just because they are younger, not just because they are at an earlier stage of evolution, but because they are in a different kind of environment, shaped by different processes, evolving according to different rules, responding to different conditions. And so the puzzle deepens, the complexity grows, the questions multiply. The mismatches are not just about expansion rates and distances. They are about formation times and masses and chemical compositions. They are about how quickly structures assemble, how efficiently stars form, how rapidly black holes grow, how galaxies merge and interact and evolve. They are about the entire history of cosmic evolution and how that history might play out differently in different parts of the universe, in different environments, under different conditions. And there are hints, faint but persistent, barely visible but impossible to ignore once you start looking for them, that the universe is not as symmetric as we once thought, not as uniform, not as homogeneous. When we look at the large-scale structure, at the distribution of galaxies across billions of light years, we see patterns that are not perfectly regular. There are regions where galaxies are clustered more tightly than elsewhere, regions where the density is higher, where structure is more pronounced. There are vast empty voids, regions where galaxies are scarce, where the density is low, where space stretches out with very little matter to mark it. There are filaments, long strings of galaxies, connecting clusters, tracing out the cosmic web, the skeleton of large-scale structure. And this is expected to some degree. The universe began with tiny fluctuations in density, ripples in the fabric of space and time. Quantum fluctuations stretched to cosmic scales by the rapid expansion of the early universe, and gravity amplified those ripples over billions of years, pulling matter together in some places, creating overdense regions, leaving other places underdense, creating the patterns we see today. But the patterns we observe are not just random noise, not just the result of amplifying random fluctuations. There are coherent structures, large-scale features, patterns that extend across enormous distances, patterns that seem to require more organization, more structure, more coherence than we would expect from the simple amplification of random variations. One possibility is that the early universe was not as uniform as we thought, that there were larger scale variations in density, deeper asymmetries, structures that were imprinted at very early times, perhaps during the period of inflation, the brief moment of exponentially rapid expansion that is thought to have occurred in the first fraction of a second after the Big Bang. Another possibility is that dark matter, the invisible substance that makes up most of the mass of the universe, is not distributed as smoothly as we assumed, that it has structure on scales we have not yet been able to detect, clumps and voids and filaments that shape how ordinary matter flows and how galaxies form. Or perhaps dark energy, the mysterious force that is accelerating the expansion of the universe, is not perfectly uniform, not perfectly constant, that it varies from place to place, creating regions where the expansion is faster or slower, where the conditions are different, where structure forms differently. Or perhaps there are other factors, other influences, other processes that we have not yet discovered that shape the large-scale structure in ways we do not yet understand. And if we live in an underdense region, if we are inside one of the larger asymmetries in the cosmic web, one of the significant deviations from the average density, then our observations are biased towards seeing the universe in a particular way. We are seeing the universe from inside a deviation, from inside an anomaly. And this shapes what we see, how we interpret it, what conclusions we draw, what models we build, what understanding we construct. And there is something almost beautiful about this, something that invites quiet contemplation, something that asks us to sit with the uncertainty, to accept the limitations, to recognize that our knowledge is always partial, always incomplete, always shaped by our perspective. The universe is not a perfect, symmetric, uniform expanse, a featureless void in which structure emerges according to simple, universal rules. It is lumpy, and irregular, and full of variations, full of asymmetries, full of places that are different from each other in subtle but important ways. And we are embedded in one of those variations, observing from a place that is, in some way, unusual, in some way atypical, in some way different from the average. And this means that our picture of the cosmos, as detailed and precise as it is, as carefully constructed as it has been, is necessarily incomplete, necessarily shaped by our perspective, necessarily limited by the fact that we can only observe from one place, from one point in space and time, from one particular location in the vast cosmic web. But this is not a reason for despair, not a sign that we can never understand the universe, not a limitation that prevents us from making progress. This is simply a reminder that understanding requires care, that it requires accounting for context, that it requires recognizing the limits of what we can observe from a single location, that it requires building models that are flexible enough to account for variations, sophisticated enough to capture the complexity of the real universe. And there are tools we can use, methods we are developing, techniques we are refining to account for these effects, to correct for our location, to infer the true properties of the universe from the biased observations we make from our particular place. We can simulate the universe in computers, creating virtual cosmos with billions of particles, evolving them forward in time, according to the laws of physics, watching how structures form, how galaxies grow, how light travels through the expanding, evolving space. We can place virtual observers in different locations within these simulations, in dense regions and sparse regions, in typical places and unusual places, and we can compare what they see, how their measurements differ, what biases arise from their different perspectives. And by doing this, by exploring the range of possible perspectives, by understanding how observations change depending on where you are, we can learn how to correct for our own location, how to account for the biases in our own observations, how to infer the true, global properties of the universe from the local, biased measurements we make from our particular place in the cosmic web. And we can look for patterns, for correlations, for subtle signatures in the data that reveal the presence of large-scale structures, the influence of nearby voids and clusters, the flow of galaxies toward or away from regions we cannot directly see. We can map the cosmic web in ever greater detail, tracing the filaments and voids and sheets that make up the large-scale structure, using surveys that observe millions of galaxies, measuring their positions and redshifts, reconstructing the three-dimensional distribution of matter across vast volumes of space. And we can use that map to understand how our location fits into the larger pattern, how the properties of our region compare to the average, how the underdensity we live in affects our observations, what corrections we need to make to account for it, and slowly, piece by piece, observation by observation, calculation by calculation, we are building a more complete picture, a picture that accounts for variations, for asymmetries, for the fact that the universe is not uniform, but complex and textured and full of structure on every scale. And this picture is richer, more nuanced, more interesting than a picture of a perfectly symmetric universe would be. It is a picture that reflects the true complexity of the cosmos, the way that simple laws operating over billions of years can create endlessly varied patterns, structures that are unique and unrepeatable, shaped by the particular history of each region, each cluster, each galaxy, each star. And as we refine this picture, as we account more carefully for our location and its effects on our observations, the mismatches begin to make sense. The puzzles begin to fit together. The galaxies that appear too massive, too mature, too evolved for their age are not violations of our models, but reflections of how distance and age are distorted by observing from an underdense region, by measuring redshifts in a place where the expansion is faster. The expansion rate tension, the discrepancy between local measurements and measurements from the early universe, is not a sign that our physics is broken, but a sign that we need to account for local variations in density, for the fact that the expansion rate is not the same everywhere. The unexpected flows and alignments, the coherent motions of galaxies across vast distances, are not mysteries, but clues to the presence of large-scale structures, asymmetries in the distribution of matter that shape how galaxies move and evolve, gravitational influences that extend far beyond what we can directly observe. And there is a kind of peace in this, a sense that the universe, for all its complexity, makes sense, that the patterns we see, however puzzling they might appear at first, are the result of comprehensible processes, laws that we can understand and model and predict. The universe is not chaotic. It is not random. It is structured, organized, shaped by forces we can measure and describe, by processes we can simulate and study. But it is also more complex than we initially thought, more varied, more full of surprises, more rich in detail and subtlety. And perhaps this is the most important lesson, the one that settles over you as you drift toward sleep, the